Hi everyone, today I'll be explaining my driverless car path finder code and which includes the graph-based path planning, which will be finding optimal route between city halls in Greater Vancouver areas. And I'll go through each part of the code and will also try run an example for you. Starting with the graph definition. So the graph here, the code begins with defining that graph, which represents the road network. And each node is a city which is represented by two-letter code. For example, we have VA for Vancouver, MI for Mission. And for each of the city, there's a list of neighboring cities along with the cost of travel between them. And these costs are basically approximated on basis of real distances. We also have a positions dictionary. So in this, we have each there is a there are like two coordinates, x and y coordinate, and these coordinates are used to compute the Euclidean distance between those two cities, and it forms the basis of your heuristic. So we have Euclidean distance function, which is used to calculate the straight line distance between two cities using those assigned coordinates to them. And this is later used in a heuristic calculation. Then we have the heuristic function, which was required, and this basically will need to estimate the distance from any node to the goal, and this would be done by heuristic function because in A star algorithm we would need this to estimate the distance from any node to the goal. And in our compute heuristic function, we have this function right here. For each city, we compute x, which is the Euclidean distance from the city to the goal, and y as a random number, which is between 5 and 10. And the heuristic value is then set to the floor of x minus 5, ensuring it is non-negative. So here we are ensuring that it's non-negative and it's set to the floor. Since subtracting a random value can result in an admissible heuristic that isn't necessarily consistent, we also include an optional iterative adjustment. So, this is an iterative adjustment which we are including. And when consistency is enforced, the code checks and relaxes the heuristic values so that for every edge, UV, the condition h of u is less than cost of UV plus h of v also holds. So we'll be checking this condition here. And then we have the search algorithms, which is the A star algorithm. I have defined different algorithms. The A star algorithm, it will use priority queue to choose the next city to explore based on the sum of the actual costs so far, which is the G score and the heuristic H. When the goal is matched or reached, the path is reconstructed by backtracking through come from map. So we will be then using backtracking from come from map. And then we have the another algorithm. And in this algorithm, it's essentially A star with zero heuristic. So the code simply creates a heuristic dictionary with zeros and calls it a A star function. Then we have is the Grassfire algorithm, which I'm doing here. So the Grassfire, it's implemented as breadth first algorithm, breadth first search, and it finds a path with the fewest hops first and then computes the total cost along that path by summing the edge weights. Then we have is the pathfinder function. So the pathfinder function is the central function which takes three arguments: the start city, the goal city, and the algorithm to use. So it will take start, goal, and the algorithm which is to be used. For A star, there is an additional option to enforce heuristic consistency. If you're using Hey star, then you can enforce heuristic consistency. And depending upon the user's choice, the function calls the appropriate search algorithm. The main part of the program prints out the available cities. It prompts the user for the start city, the goal city, and the algorithm which they want to choose. And for A star, it asks if they want to enforce consistency or not. Finally, it displays the path and the total cost which is found. So now if I dry run this, I get this. So I start with the city. Suppose I'm choosing Vancouver. I am choosing my goal city to be Mission. And then my algorithm is, which I'm using is A star. And if it says if I want to enforce a consistent heuristic, then I say yes to it. and then it gives me a path which is found, and it also gives me total cost. So this is how it works. It computes the heuristic values for each of the city using compute heuristic function, and with that consistency in force, it iteratively adjusts these values so that the condition for the A star is satisfied. And the A star algorithms then starts at VA. It explores the neighbors such as in NW and BU by calculating the tentative cost from the start and then adding the heuristic of each of the neighbor. Through a series of expansions and updates, the algorithm it also finds the best path from VA to MI. So the best path which is found is VA, NW, DE, LA, AB, and then mission. And the total cost is 90A. This means that it chooses a route which is starting from Vancouver, going through New Westminster, then it's going through Delta, Langley, Abbotsford, and finally reaching Mission. And the total cost accumulated along with this route is 90A, which is calculated by summing the individual edge costs. In summary, this code builds an offline road network graph and uses three different search algorithms, which is A star, Dijkstra, Grassfire, to find optimal paths between cities. And the dry run demonstrated how the A star algorithm, especially with the consistent heuristic, if you're using consistent heuristic, it can effectively determine the best route with the total cost of 98 from Vancouver to Mission. Thank you.